Hi guys, this is Mr. Y. Today we're going to be talking about learning the difference between observations and inferences, and also the basics of some experimental design using the following vocabulary of hypothesis, independent variable, and dependent variable. So let's get started. Now in biology, observations are highly important, more so than most other sciences, because for many practical reasons, there are some things we really just can't study in the lab. They're either too big, they're too expensive, they just don't handle well in captivity. So a lot of the earliest stuff we know about biology comes from observations, and then confirming those observations, and then triple confirming those observations before any experimentation has ever been done. So with biology, you really have this duality that you don't see in many other sciences, that includes observations and experimentations, whereas a lot of the other sciences, physics, chemistry, they'll stress more experimentation. Now, the thing about observations is there is always a need for a high degree of accuracy. So what do I mean by that? Well, if you look at the picture over here on the left, you can see that whoever the gentleman was who drew this lovely little diagram, obviously he was a very skilled drawer. He just was not very accurate in his observations of an actual giraffe. I would wager he probably never even actually seen one. First notion is the scale is all wrong. That gentleman there on the left of the giraffe is almost up to the height of the knee, and he looks to be a full-grown adult. So based on that, this giraffe would be bigger than any giraffe I've ever seen, ever. You can see again the head of the giraffe looks more like a horse than it does an actual giraffe. And yeah, this drawing is not what you would consider to be a very accurate observation of a real-life giraffe like you see on the right-hand side. So being very good at observations is highly important for biologists. So what is an observation? An observation is receiving knowledge from the outside world through your five senses: sight, sound, taste, touch, and smell, or using instruments like microscopes or telescopes or any other instrument to make recordings of data. So things like Geiger counters that record radiation even though you can't see, touch, taste, smell it. All that stuff counts as an observation. Whereas an inference is to basically reach a conclusion based upon what you know. Now, this is usually based hopefully on facts, and hopefully those facts are right, but maybe they're not. So it's kind of like making an educated guess based on what you believe to be true. So to help us along with this, I've put in a few cartoons to test out your skills in getting the differences between observations and inferences down. So in this cartoon, a simple question for me might be something like, what are three observations you can make? What do you know for sure is actually true based upon this picture? Well, you know, for instance, that it is nighttime. You can see the moon and the stars out there behind them. You know that these cows, and they appear to all be cows, these cows are apparently running. You can see the smoke behind them here. You know that there is a hat, and that there is looks like a coffee pot, if I was to guess, on this one cow's leg. Now, alternatively, you could also ask, well, what's the inference from this? Well, the inference comes from understanding the whole picture. The inference being, well, the cows are running, and based on the facts of that coffee pot being stuck on his leg, the hat in the air, and the dust cloud behind them, maybe these herd of cows were running along and ran through somebody's camp. Again, we don't know that for sure based on this picture. There's just not enough observations. But that's a pretty good inference. So an observation is what you know to be happening. An inference is what you assume to be happening. Another example, this little comic strip. In the first slide, we see Calvin here. This is from Calvin and Hobbes. He says, "For show and tell today, I have something that will astound and amaze you. This little guy can," and then we skip to the next slide, and you can see him looking down into the bag, and then he's looking around in the third slide, and then he says, "Have you all had your shots?" Now, just for clarity's sake, I'm going to erase this thing here. That's just the author's signature. That's not actually part of the cartoon. So what do we know to be happening? What is the observations we can make from this cartoon? Well, he's obviously speaking to somebody. He obviously is, he's got a paper bag in his hand. He's got a striped shirt on. In this slide here, he's looking into the bag. And then in this slide here, he's looking back and forth all over the place. And then, again, he's talking to somebody. He has the bag down here in his one hand by the end. What do we assume to be happening? Well, we assume because he's talking to somebody, and because of the way he's talking in the first slide, he says, for show and tell, we assume he's talking to his classmates, his school. And he says, this little guy, so we also can assume that whatever was in the bag, or whatever he thinks is in the bag, is probably a little bit alive, probably a little bit, creepy crawly, who knows. And we can also assume that when he looked in the bag, he expected to find the guy. And then when he didn't find the guy, that's when, once again, he began looking left and right over here in the third slide, looking around saying, where is it, where is it, where is it? And we can also assume that whatever this little guy was, it's somewhat dangerous enough to where Calvin has to warn all his classmates, hey, have you all had your shots? Because, this thing might actually cause you to need them. One last try at this. Excuse me. We have Calvin once again, and he's talking to his dad. And you can see them in the first slide. He says, new hat, Dad? Dad says, yep, I like it. Thank you, so do I. And then you see Calvin in this third slide making a spherical object out of some kind of white powdery stuff. And then in the fourth slide, you see the dialogue box and a hat and a briefcase on the ground. And it looks like the remnants of snow down there. And the dialogue box says, you're going to be late for work, Dad. So what do we actually observe from this strip? Well, both Calvin and his dad are dressed for cold weather. His dad's carrying a briefcase, has a hat on. Calvin, of course, has his little beanie hat on. You can see Calvin is looking at his dad, and his dad appears to be walking away from him. And once again, Calvin is looking somewhere. Looks like he's still looking towards his dad a little bit by the way his head's twisted. And then the next slide, we don't see anybody. It's just the dialogue box and then these two items once again. So what's the big inference? What do we assume to have happened? Well, he says, hey, Dad, nice hat. He says, I like it, thanks. And the whole time, Calvin's just eyeing that hat, saying, oh, well, let's see if I can hit it with the snowball. Hits his dad with the snowball, and what's his dad do? His dad run away? No, his dad ran back after Calvin, causing Calvin to scream out, saying, you're going to be late for work, Dad. You better stop chasing me. So that's inference versus observation. We're going to move on to experimental design now. And experimental design tends to be one of those things that comes up a lot in science, especially if your intention is to do science fair. And while you might have a very good idea for an experiment, if you really mess up the design, even if your idea is good, you might not get what you expected in terms of results. So experimental design can really have a big influence on your results, because if you have one bad design, you might miss what you were looking for. Okay. So with any type of experiment at all, you want to make sure you have a decent hypothesis. Now, a hypothesis must be a specific, that means testable or measurable, statement of relationships among things. At this level, we usually say they must take the form of if blah, 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 then blah, 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 blah. And it can be seen as kind of a prediction. So, for example, if plant growth is related to the type of soil that it has, then exposing plants to unhealthy soil will result in changes, to plant growth. It's very specific and it's testable. It's very predictable in how we expect the outcome to work. Another example, if skin cancer is related to ultraviolet light, UV light, then people with a high exposure to UV light will have different rates of skin cancer. Again, very specific, and you can measure that. So it can be testable or measurable, either way it works. Another example, if the speed of gravity is related to an object's height above the ground, then the greater the height, the faster it should travel when dropped. Again, this is a little bit more complex, but it's still very specific, very testable. This example, if I eat chocolate, then I will get pimples. Yeah, that's way too simple. So, here is, once again, Calvin, and we see him in these slides, and if you take a minute and read through, you can see he's got a snowball, it looks like. He looks like to be on top of a hill. He rolls down the hill. He's watching. He gets excited, and you look down, and you see Susie, the poor little neighbor girl there, crushed by a big ball of snow. So the question I posed was, what could Calvin's internal hypothesis be in this case? The one I came up with, and yes, it may not be as simple as yours, but the one I put it in is an if-then format, is if the amount of snow compaction, the amount of snow that builds up, is related to the length that a snowball travels, then rolling a snowball down a long hill should be enough to knock down the neighbor girl. Again, Calvin thought about this, and then he said, I can test that, and much to Susie's dismay, it worked. So in any experiment, there's going to be two different types of general categories for variables. There's the independent variable. Oftentimes in different textbooks you'll hear this called the manipulated variable. That is the factor you're actually changing for the purpose of your experiment. The best way to identify the independent variable is asking yourself, okay, what am I messing with? What am I making different? What am I screwing with? What's the thing I'm really changing between my control and my experimental groups? And we'll get to those two terms later. Almost everything else is going to be considered a constant except for your dependent variable. Oftentimes this is called the responding variable. I like the terms manipulated and responding variables better. They're much more self-explanatory. But the dependent variable is what you're measuring from your experiment. You basically have to ask yourself, how am I going to actually be recording my results? What will I be measuring? Will I be measuring length? Will I be measuring time? Will I be measuring distance? Will I be measuring weight? What will I be measuring from the general experiments? That is your dependent variable. So for example, going back to one of our original hypotheses, if plant growth is related to the type of soil that it has, then exposing plants to unhealthy soil will result in changes in plant growth. So, my independent variable, my manipulated variable, the thing I would change is the type of soil. I would be making the soil unhealthy in the experiment. The thing I would record, my dependent variable, my responding variable, I would record or measure the growth of the plants, either by their leaves or their stems, however I decide to do it. So you have to set up in any experiment a comparison basis, because without a comparison you really don't know how much things have changed. We generally call the comparison group the control group. So it's a parallel experiment that you do at the same time as your experiment that shows you what would happen without you screwing with things. So basically running a parallel experiment without changing your manipulated variable. So it gives you a basis for your results. And you can see this here when you have the healthy soil, that's your control, and the unhealthy soil, that's your experimental group. So again, this is the same exact hypothesis we were just working with. So the experimental group, again, this is the experimental, this is the control, is the one we've actually changed. So again, the healthy soil has not had anything changed, anything different at all, except for the soil itself. Now this graph comes from an experiment. I have no sense of exactly what it is, but what you can see is the results from their control over here on the left and their experimental groups. And you can see on the top they have a nice key of before and after. So in their control groups, before whatever happened with their experiment, they were at 12.1. After, it drops to 9.8. So doing nothing causes it to drop from 12 to about 10 by 2 points. In the experimental group, you can see before it's at 28, after it's at just over 3.5. So whatever it was they changed caused this whole thing to drop a lot. That gives you a much better basis for comparison, especially when you compare it to just this little change here. That's why you run a control group. Constants. Constants are factors in your experiments that are not changing between either the control group or the experimental group. So these are the things that are always staying the same between the two of them. So to figure them out, you just got to ask yourself, what am I doing for both of them exactly the same every time? So in our example here, you would want to make sure you keep the same plant species. You want to make sure it's got the same basic age, and so you plant them at the same time. You want to make sure you give them about the same type and amount of food, that is to say planting food, not, food is for plants is sunlight, but the same amount of water at the same time of day, the same amount of sunshine. Place them in the same room. You want to make sure you allow both plants to grow for the same amount of time. You want to make sure everything else is equal, so there can be nothing else that could be a cause for any difference except for your manipulated variable, the soil, because you want to see that as the root cause of any big changes that you find. So in any experimental design, at some point you're going to have a results section and a conclusion section. So first we're going to deal with the results. The what happens. The why comes later. So the results is the actual data you recorded. Usually you can show this with tables and graphs, but these are pure facts that came out of your experiments. You can talk about trends like increasing or decreasing that you see from your data, but it must be pretty easily observed. Results, remember, are not your opinions. That's going to come later in your conclusions. So results are just saying, oh, this pattern decreased, or this pattern increased, or this changed this way, or this changed this way. It's not saying why it happened, just what happened. And again, you can see this graph comparison here. It shows the letter grade in the class, F, D, C, B, A, and then the number of emails per student towards the teacher. So the F students are much more likely to be sending emails to the teacher. The why, the conclusion section of your experimental design, is where you put in why you think what happened. So why did things occur the way they did? You must make it clear if you think your original hypothesis was either supported or rejected in this section. Keep in mind, you should never use the word proved. Never, ever, ever use the word proved. You can either support or reject a hypothesis. If it's supported, you should probably make statements as to how you could test this even further. If it's rejected, that is to say, if your hypothesis was just proven completely wrong, you should be stating why you think the results came out the way they did against your hypothesis. And it's okay to have a hypothesis that comes out wrong. That's the nature of science. So remember, there is no guarantee of finding what you want with your experiments and the way they're designed. You can only have a good design and just see what happens. That's the fun part about experiments. Revisions are always going to be a common fact in the work of science. That's a simple, basic idea of all science. You can see these quotes from Edison's. Keep in mind, he did a lot of experiments when trying to invent his first light bulb, and lots of times he failed. So that's it for this presentation. If you guys have any questions, talk to me in class. Otherwise, make sure you've taken good notes.